So generally, in a 3-day period, you're going to come in contact with about 20 people. Let's say that you're one of those 20 people. Let me step back for a minute. In herd immunity, if 95% of the population is immunized, that is going to provide herd immunity. So we're looking for 95% immunization. That means that just 1 out of 20 people has not been immunized. The other 19 people have been immunized. So if you come in contact with 20 people in a 3-day period, and this is, they've estimated on average, that generally in a 3-day period, you're going to come in contact. When we say contact, we mean close enough that the disease can be spread. That means either shaking their hands or within 3 feet of being coughed on or something like that. So if you're one of those 20 people that has not, or you're one of the 20 and you're the one that has not been immunized, well, you're somewhat protected because these guys are not going to get sick from a disease that moves through the population. So if they come in contact with it, they're okay, and so you're somewhat protected. However, let's suppose that these 20 people you came in contact with, and these 19, and the 20th one you came in contact had the disease, okay? So now you get sick because you came in contact with this individual that wasn't immunized and they passed it to you, but now the other 19 you come in contact with, they're going to be fine, they're going to be healthy, and the disease stops. All right, now let's assume that our immunization rate is only 85%. So instead, we're immunizing 2 less people in our population of 20. This individual here and this individual here now, we're not immunized. Okay, so when you, having gotten sick from this individual, go and meet the 20 people that you come in contact with, you're going to spread that disease to these 2 individuals that have not been immunized. These 2 individuals then go out and they're going to meet 20 people as well. Again, only 85% of the population is immunized. So the people that they meet, 2 of them, they're going to transfer the infection to, and it's just going to continue on through the population. When you see your vaccination rate drop down to 90 to 85%, herd immunity kind of goes away. And here's the problem with that. And here's why you want to stress vaccination, immunization. Who are these people generally that are susceptible, that have not been vaccinated? They're usually the very young, babies, and the elderly that have weakened immune systems. So for instance, we had whooping cough move through California just last year, and it required the state, or that caused the state to require all grade school children to get immunized for whooping cough, even if they had already been immunized previously. What happens is, if you are a healthy young adult, this individual here, and you get whooping cough, there's a good chance that you're probably going to survive. Your immune system's healthy, you exercise, you eat right, you'll do fine. You might get really sick, but your immune system will recover and you'll probably survive. But before you got really sick, you came in contact with a couple of individuals, and this one here happened to only be 6 months old. And so you exposed it, and we can't immunize babies. You know, their immune system's not ready for immunization. And so this child dies because we didn't maintain our community immunization rates that we needed. When we look at the death rates of whooping cough that moved through California last year, those that were dying were babies and young children that hadn't been immunized yet, hadn't had a chance to get immunized. So the reason we want to maintain a high vaccination rate is to protect those through herd immunity that don't have immunity or can't get their vaccines yet.
Do you know why there was a decrease in the vaccinations?
There are a lot of factors that can play into that. A lot of times it can be cultural, it can be religious, it can be economical. there are a number of factors that can contribute into decreasing immunization. It can just be complacency. You know, a lot of times when you've not heard of a disease in a population for quite a while, it's been depressed, parents stop getting worried about it. They stop immunizing children, and so you see the immunization rates start to decline. So there are a number of factors that can contribute to it. Yeah. And we see that in the United States with our immunization rates ebb and flow depending on various factors, but complacency being one of them for sure. Any questions, comments?
Do you see, as far as the parents concerned with autism now and immunization?
There's no evidence to support any kind of autism claim there.
Yes, I know that was the thing, like, I've never really, researched it myself, but I immunize my kids.
Yeah, I know that has been in the media cycle for a number of years, and every time somebody comes up with a new claim, it's refuted. Science has demonstrated time and time again that vaccinations do not cause autism. And in fact, autism is generally caused by a brain condition, either in the amygdala or the hippocampus or the connections between them. It's a developmental condition that can be brought on by a number of things, but we've just seen recently in the newspaper that obesity seems to contribute to autistic rates. There's been a 65%, women that are obese during pregnancy see a 65% increase in autistic rates in their children.
If we go back to the joint thing, so is that the reason, like, every time when I'm trying to go back to Africa, they give me all kind of vaccination, all kind of medicine, all kind of...
I'm sure to protect you, and again, the vaccination rates probably are not as high, so the herd immunity that you would see in those communities probably not as effective, and so your risk is greater, and I'm sure that's why you're being given vaccines to travel.
Yeah, but when we come in here, they don't do that.
I'm sorry?
When they have like new immigrants coming here, they don't do that.
I don't know, I'm not sure of the policies. Yeah, I'm sure that they get vaccinated for certain things. I don't know. Huh?
I
No?
didn't get anyone else.
Well, get on it.
You, like, are you serious?
Nah. Let's keep praying here.
Okay, so let's talk about the different types of vaccines. There are two general categories for vaccines. Attenuated vaccines and inactivated vaccines. Now, an attenuated vaccine is a live organism. It's a weakened form of the disease, and so it's going to replicate inside your body. So when you're given this vaccine, the organism is going to grow, reproduce. This is going to be an active immunity then. Your immune cells are going to respond, your B cells, T cell immune response. The way they create attenuated vaccines is a lot of times they'll grow the microbe until they weaken its virulence response. You know, they grow it in different media. They grow it until the DNA becomes mutated. Or at least that's how they used to do it. Now they use recombinant DNA and genetics to knock out the virulent gene. And so you get exposed to a live agent that is actually missing the epitope that's on the surface that would cause the disease, or the virulence factor that would cause the disease, I should say, and the epitope is still there. So let's imagine that if your bacterium here has on it, a specific section that is recognized as the antigen. In the gene, if we knock out the gene that causes the virulence, now when you get exposed to this microbe, your body will respond to the antigen, and you don't have to worry about the microbe causing you illness because we've knocked out the gene that causes the virulence. Prior to this method of creating attenuated vaccines, and maybe even still now, but much, much less so, there was always the risk when giving a live organism that you could cause the person to get the disease. You could get sick from it. It wasn't uncommon for individuals when given a flu shot or something to have mild symptoms of the flu simply because you're being given an attenuated vaccine. What are the advantages to this kind of vaccination? It's going to be very long-lived, maybe even the rest of your life. And you can spread it to others. Because you're talking about a live organism, you have the risk of transferring it to others, either by coughing on them or you having it on your hands and transferring it that way. So attenuated vaccines can be transferred to others. The problem, as I've already mentioned, or the disadvantage, is that there's a potential for disease, much less so now than when we first started using attenuated vaccines. And because we're talking about a live organism now, they require refrigeration. Why is that an issue? Well, you've got to get the vaccine to the people that need to be vaccinated. And a lot of times, that can be difficult, especially when you've got to keep them under refrigeration. So what about inactivated vaccines? Now these are vaccines or organisms that are unable to replicate. So because they are unable to replicate, there is no amplification of the dose. See, with attenuated vaccines, because these microbes are alive and they're replicating, there is an amplification of the dose, if you will. You get exposed to a greater volume of organisms simply because they are replicating, and so this creates a somewhat increased immune response. With inactivated vaccines, you don't get that inflammation of the immune response. And in fact, many times, in an activated vaccine will require a booster. So with these inactivated vaccines, you can take one of two forms. They can be the whole agent, where they've killed the microbe, so you're being exposed to the whole agent but it's dead, or most often a fragment of the microbe. As long as this fragment contains the epitope, that part that's going to be recognized by the immune system, then the fragment will serve to stimulate the immune response.
Is that booster like a booster shot?
Exactly. That's exactly what we're talking about. So types of inactivated vaccines, what we have are killed microorganisms. Again, or inactivated viruses where you've killed the organism but you've retained the epitope. If you damage the epitope, then it's not going to be effective. The immune system won't recognize it. toxoids. Again, these are going to be inactivated toxins where, assuming again that maybe this becomes the epitope and this is the part that causes the toxic effect, if you can knock out the toxic part of the toxin and retain the epitope, then you can get the response, the immune response we want. Protein subunits. Here we're taking fragments of the infectious agent. So maybe it's a protein that the microbe produces. Hepatitis B is controlled this way. The gene is given to a yeast cell. The yeast cell produces the protein, and then the protein is used in the vaccine. Now, many of these require what is called an adjuvant. And this is something